Now I'm going to talk a little bit about equivalence relations. All right, recall that R is an equivalence relation in case what? In case it's reflexive, symmetric, and transitive. Okay, so any relation on a set X that has those three properties is an equivalence relation. Now, given an equivalence relation, we can define what's called an equivalence class. And so we pick any element in the underlying set X. The equivalence class of that element, let's say A, is the set of all X's such that I have an ordered pair, A comma X or X comma A in R. All right, so what's an equivalence class of A? It consists of all elements that are in an ordered pair that has an A in it. So let's see how that goes. All right, let's look at a previous example, R8. R8 was our equivalence relation, AA, BB, and CC. Those three ordered pairs. So how do I figure out what the equivalence class of A is? Well, I look at all ordered pairs that have A in it. There's only one. And the second element goes in the equivalence class of A. So the equivalence class of A is just the set A. The same token, the equivalence class of B, well, there's only one ordered pair that has a B in it. I have to put the other element in that set, and that's B. So the equivalence class of B is the set B. By the same token, in this case, the equivalence class of C is the set C. Now let's look at another equivalence relation, AABBCC, AB, and BA. And let's find the equivalence classes. Well, the equivalence class of A consists of all elements where I have an ordered pair that has an A in it. So if I think about that, there's one ordered pair with an A in it. That tells me I need to put an A there. But I have this other ordered pair with an A in it, right? A comma B. So I need to put a B in that set. And in fact, that completes it. So the equivalence class of A is just the set AB. By the way, if I'm finding the equivalence class of B, I look at all ordered pairs that have a B in it. And any element that's in that ordered pair has to go in the equivalence class. So I see I've got to have a B and I also have to have an A. So the equivalence class of B is also the set AB. Notice in this case, the equivalence class of A is exactly the same as the equivalence class of B. By the way, if I compute the equivalence class of C, I look at all ordered pairs that have C in it. There's just one. And I have to put all those elements in here. Well, that just turns out to be the set C. Okay, so given this equivalence relation, here are the equivalence classes. Notice that the equivalence class of A is exactly the same as the equivalence class of B. Those two are equal. Now, remember what a partition was? A partition of a set A, or a set X, has to satisfy three criteria, right? One is the null set can't be in there. The other is, another one is that when you union them up, you've got to have everything. And finally, there is no overlap, right? And if you look at the set of equivalence classes up here, which are just, they have two subsets, the set A, B, and the set C. If you look at that, you realize that in fact that forms a partition. And in particular, we have a theorem that says every equivalence relation gives rise to a partition, and every partition gives rise to an equivalence relation. So if you want the number of partitions of a set, it's the same as the number of equivalence relations on that set. And the point being, partitions are a lot easier to count than equivalence relations. So let's see how one would go about if I start with a partition. How do I come up with an equivalence relation? Up here you'll notice I started with an equivalence relation and I ended up with a partition. All right, but let's start with a partition of this set Y, 1, 2, 3, 4. Well, one partition would be this, right? The set 1 and the set 2, 3, 4. It satisfies all criteria for a partition. And I claim that gives rise to an equivalence relation. Okay, how do I write down the equivalence relation associated with that partition? And the answer is, I look at every one of these subsets, and if an element is in the same subset as another, then its ordered pair goes in the equivalence relation. Let me say it again. If an element is in the same subset as another element or itself, then the ordered pair goes in the equivalence relation. So let's look. There is one subset of the partition. Since 1 is in the same set as 1, that's going to be my rule. The ordered pair 1, 1 is in my equivalence relation. Now I go to the next set. Since 2 is in the same subset as 2, I get the ordered pair 2, 2. Since 3 is in the same subset as 3, I get the ordered pair 3, 3. And since 4 is in the same subset as 4, I get the ordered pair 4, 4 in my equivalence relation. Notice also, since 2 is in the same subset as 3, I get the ordered pair 2, 3. By the way, 3 is in the same subset as 2, so I get the ordered pair 2, 3. Or 3, 2, right? 2 is in the same subset as 4, that gives me the ordered pair 2, 4. 4 is in the same subset as 2, that gives me the ordered pair 4, 2. 3 is in the same subset as 4, that gives me the ordered pair 3, 4. But notice 4 is in the same subset as 3, so that gives me the ordered pair 4, 3. And that's all my ordered pairs, and I claim that if you look at that relation, which I got by analyzing this partition, it is an equivalence relation. An equivalence relation is reflexive, symmetric, and transitive, and I claim it satisfies all of those. Notice, transitivity, I have a 2, 3, and a 3, 2. Transitivity would require me to have a 2, 2, but I got that. I have a 2, 4, and a 4, 2. Transitivity requires a 2, 2. I got that. I also have a 4, 2, and a 2, 4. Transitivity requires me to have a 4, 4, but I got that. In fact, I claim that if you check all the properties, this R1 turns out to be an equivalence relation. That is both reflexive transitive, and symmetric. And I think I'll stop there.